All right, so this, oh goodness gracious. All right, so this is part B, and this is the first part. So deriving the Fensky equation for determining the minimum number of stages. So find the Fensky equation. We're going to assume relative volatility of a binary ideal mixture. So what does this mean? This means we have our ideal Raoult's law, so x times p set equals y times p. And then it also means that the heat of vaporization of our lighter component just about equals the heat of vaporization of our heavier component. And that's important because when we derive the term for alpha from the Clausius Clapeyron or just Clapeyron, I don't remember. But when we derive the term alpha, that's derived from, I think, P set of our more volatile component. Set J. So that assumes that not the individual p sets, but when the p sets are divided by each other, it assumes that they're not a function of temperature. And we derived that, I think, in homework 1 or 2, but I'm not going to derive that again. But alpha is also equal to yi times p over xi. And then yj times p over xj. P's cancel out. This is the same thing as ki over kj, which we call our partition coefficient, which is also going to be important because ki by itself equals p set I over p, which equals yi over xi. And that's at any stage where it goes to equilibrium. So ki times xi at a certain stage equals our vapor mole fraction at that same stage. Okay, so jumping into the Fensky equation, it's used to find the minimum number of stages required to reach a certain distillation composition. So we want to get to a certain distillation composition. So let's say it's like 0.99. We have our 45-degree curve. We have our equilibrium curve that's not written too well. So if we're trying to get to here, if it's focusing, the point that requires the least number of stages is when we would have an operating line, and our operating line, at least if we're looking at a rectifying stage, that's going to follow the formula of yn plus 1 equals xn r over r plus 1 plus our distillate composition over r plus 1. So the least number of stages would occur when our operating line falls right on this 45-degree line. So then we would get the least number of stages that we would need in order to get there. So what do we have to do for our operating line to have a perfect 45-degree line? what we'd have to do is we would have to make the slope of this function equal to 1. So that happens when you take this r over r plus 1 term and you make it 1. So in order to do that, you would have to make r, so r plus 1 limit of r would have to go to infinity, because this term can never actually reach 1. It's always going to be less than 1 no matter what. But if you're approaching infinity, then you're going to get this bad boy to about 1. So how do we get it to 1? Well, r is comprised of the liquid that we put back into the system after it goes into the top of the condenser over the amount that's actually being taken out. To make this term go to infinity, we would have to make L go super big and then D be super small. So basically our D would be 0, R would be infinity. So this term right here would end up equaling 1. This term right here would end up dying because you'd be dividing by infinity. And you would be left with y n plus 1 equals xn. Alrighty. Well, what we can do from here is we can take our partition coefficient. I think that's, yeah, partition coefficient. And we have the general formula of ki times x at any stage equals y at any stage. Well, what we could do is we could say ki times x of n plus 1 equals y of n plus 1. Well, now we can substitute what we have right here in for y n plus 1. So k1 n plus 1. X n plus 1 equals xn. Let me flip the page because we're running out of room. Okay, let me rewrite this. N plus 1 equals xn. Okay. Let me notate this as ki, because right now we're working in terms of our more volatile component. But what we can also do is we can say kj of x2, which is our less volatile component, n plus 1 equals x2n. So then that would indicate, or that would imply that this is x1 and x1 n plus 1. So we will take this and we'll divide both of these equations by each other. So we have x1 of n over x2 of n equals ki over kj x1 n plus 1 over x2 n plus 1. All right, well, we know that our ki over kj term is alpha. And then we have the same thing right here. So x1 n plus 1, x2 n plus 1. All right, so now let's plug in actual values for our stages starting at our condenser stage, and we're going to derive something here. So we have x1 at stage 0 over x2 at stage 0 equals alpha x1 n plus, oh wait, no, x1 at stage 1, no more n's, x2 at stage 1. Okay. And then let's do this for the next one. So x1 at stage 1, x2 at stage 1 equals alpha times x2, or no, x1 at stage 2 and x2 at stage 2. Well, we can keep doing this over and over. It kind of follows this chain where it would go like and then x2 would be over here. And basically what you're doing over and over again is multiplying by alpha. So if I substitute what I have in here for x1, if I throw that up or x1 at stage 1 over x2 at stage 1, if I substitute that in here, we have x1 at stage 0 for x2 at stage 0 equals x1 at stage 2 over x2 at stage 2 times alpha squared. So we can see from this that this then follows the general formula of x1 at our condenser stage over x2 at our condenser stage equals alpha raised to the power of whatever stage we're working at over our more volatile component or light key. Come on, focus, buddy. There we go. Where was I? I lost my train of thought. Oh yeah. In more volatile component, less volatile component at stage N. All right. So we'll solve for N, and that's the number of stages that we're looking for. So we'll divide both sides by x1 at stage N over x2 at stage N. Equals alpha naught. Okay, then we will log both sides. So log of A or alpha raised to N. And then I'm gonna log this thing. This is a big term. I don't feel like rewriting it all. And when we log this, we can pull N out to the front. And then we can divide this side right here by alpha. So we end up with N equals the log of this entire term, and I'm not going to say it because it's a mouthful, divided by the log of our alpha. And that's our Finsky equation. All right, so this is going to be the next part, which is deriving the Underwood equation for minimum reflux. All right, so here's what we have going on. We have Underwood. So we have our equilibrium line between our high key and our light key. Our heavy key and our light key. And let's say we have a certain distillate composition, and we have our operating line from there. So then we draw our steps in our McCabe-Thiele graph. And as we get, I can't really zoom in, but as we get closer in here, like each step is a number of stages. Well, at this pinch point, it could really go on for forever. So we could have an infinite number of stages at this point. So if we do our mass balance for our rectifying and our stripping stage, so for rectifying, we have V y n plus 1 equals Lxn plus xd times d. And then for our stripping, we have L bar xn equals V bar, times yn plus 1. Plus xb times b. All right. So what we say right here, and this applies for the stripping equation as well. So, gosh, that's not good stripping line. All right, I'm not even going to bother with the stripping line. But like we said, the number of stages goes to infinity. So we'll start with our rectifying stage. So on our rectifying, we have V and then Y of our light key at stage infinity equals L x infinity plus xd times d. And when we have liquid and vapor compositions at different stages, we can only relate them with the operating line. But since they're both at stage infinity, it eventually gets to the point where they just don't change. So we can apply the equilibrium relationship because we're saying that they're essentially at the same stage. And we can use Routh's law, or more simply, we can use the partition coefficient. So the partition coefficient of our lighter element equals yn over xn. So we'll say this also equals y infinity over x infinity. So then x infinity equals y infinity over ki. Focus up for me, buddy. Come on, you got it. All right. So now we can plug this in for x infinity. And we want to solve for y infinity. So we'll go ahead and move this over as well. So we have v y infinity minus L times y infinity over ki equals xd times d. We'll pull out our y infinity, and then we'll divide what's left over onto this side. So then we have y infinity equals xd times d over v minus L over ki. Let me double check and make sure that I did the algebra correct. Yeah, that should be it. All right, so what we can do here is we can take the summation of these, so sum each side, and we know that the summation of our vapor mole fractions simply equals 1. So that equals 1. What we'll do is we will multiply both sides by v. So we have v equals were we supposed to substitute? So multiply both sides by v. So we have v times xd times d, v minus lki And then on this side, we will divide we'll divide the numerator and the denominator by v. So we'll clean it up a little bit. So then this leaves us with summation of d1 minus lki over v. And then we will multiply, oh gosh, focus on for me, buddy. And then we will multiply the top and the bottom by ki, summation of ki xd over d, ki minus L over V. And then for the last step for our rectifying stage, we will divide the top and the bottom of both of these by the partition coefficient of our heavy key. And when we do that, we're left with some terms that are ki over kj, and that's equal to our alpha term. kj times v. All right, and then we have this term right here. So we're just going to call that, we'll call that our phi. Combine all of those terms together, and we have alpha ij kd times d alpha ij minus phi. So we are basically going to do the same thing for the, and all of this is equal to v. We're going to do the same thing for our stripping section. So we have Lx at infinity equals, and these are all bar. Y stage infinity plus xb times b. And then we'll do the same thing. So we know that ki equals y infinity times x infinity, and we'll solve for x infinity. So x infinity equals k infinity over ki. So plug that in here, and then we will want to solve for y infinity again. So we have L bar times y infinity ki minus v bar y infinity equals xb times b. All right, pull out our y infinity, and then we'll divide this side by this. So y infinity equals xb times b over L ki minus v bar. We'll switch our numerator and we'll just switch the signs on our, shoot, I can't talk, on our denominator to make it look more similar to our rectifying equation. And we have negative xb over v bar minus lki. So that equals our y infinity. So we're going to do the same thing that we did last time. We're going to take the summation of these. We're left with 1 equals the summation negative xb, and then we're going to pull out the negative soon. V bar minus lki. I'm going to move the negative over to this side. And then we'll divide our, I'll move the negative over, and then we'll multiply everything by v bar. So we have negative v bar equals the summation of v bar xb times b over v bar minus lki. All right, so then we'll divide the top and bottom by v bar. Negative v bar equals xb times b. 1 minus L v bar ki. We will then multiply everything, or we'll multiply the top and the bottom by ki, and then we'll divide the top and the bottom by kj. So that does the same thing that it did to our rectifying equation. That gives us alpha ij xb times b over alpha ij minus L bar over the partition coefficient of our heavy key over V bar. And then similar to what we did last time, we'll call all of this term right here omega. All right. So let's pull back up what our equation for our rectifying section was. That was alpha ij xd times d over alpha ij phi. So I can't explain this next part, and even Mr. Carlos says that he can't explain this next part, but we're able to combine these equations under the application that our omega equals theta and our phi also equals that, which means our omega equals our phi. So we'll plug theta in for both of these, and then we'll have common denominators on both of these equations, and then we'll subtract them from each other. So that gives us, right, no, we'll just add them to each other. So that gives us v minus v bar equals alpha xd d over alpha minus theta plus, and sorry, these are all the summations. That has not gone away. And then alpha xb times b. All right, and then we can find these fractions. Summation of alpha xd times d plus over alpha minus theta. All right. So this is what we're left with. And we can apply our overall mass balance to this equation. So we know that this right here is the same as, or I guess if we do our mass balance at our feed for our vapor product, we have 1 minus Q times our feed equals V minus V bar. So we can plug that in right here. So we have 1 minus Q times F equals the summation, and then we'll factor out our alpha term. So alpha aj times xd times d plus xb times b over alpha ij minus theta And we know that this right here is the mass balance of our overall mass balance when we have it with respect to our light key. So this right here all equals Z times F, or Zi times F. We have the summation of Aij Z I F Aij minus theta. We can divide both sides by F. And then that finally leaves us with our Underwood equation, which is 1 minus our quality equals the summation of Ij times the composition of our feed over alpha Ij minus theta. There we go. So this is our last part, and this is using our Underwood equation to find the minimum reflux ratio. So here's what we have going on. We have an equimolar mixture going into our feed, and our feed is 100 moles. Then our equimolar mixture, so that means we have an array of 4 components, and they're equimolar, so they're all 0.25. 0.25. Gosh, I'm getting my decimals and my commas mixed up. KS's. No, that's not what our KS is. Relative volatility, so that's our alpha terms. So alpha equals NP dot array. Well, we need, I'm guessing we need these to go in order. What order would we? Yeah, I guess if you, no, you'd want to go from lightest to heaviest, and I'll go back and double check that, but I'm pretty sure. Oh wait, no. It's. Oh, okay, yeah. If it's higher, then it's more volatile. So yeah, it would be in this order. So this is our heavy and light key. Oh shoot, come back. And then our recoveries, which we notate as RD, those are going to be NP dot ES. That's the array that we want. All right. But, oh shoot, I didn't make a bracket. Excuse me. All right. And then also we'll need the term Z times F. So we're going to make that Z times F. All right. So now we'll define what our Underwood equation is. In front of me, I just have the paper where we, let me pull this up. I just have the paper where we derived or the last part of deriving our Underwood equation. So we'll be using that just so I don't have to try to do, so I don't have to pull from memory what I just did 5 minutes ago. So our Underwood equation, define Underwood, and that's going to be, so it would be a function of our alpha, our feed composition, and our theta. But since we're defining those for this problem, we're just going to make it a function of theta. And that's going to be equal to P dot sum of our alphas times our z's divided by alpha minus theta. We forgot a parentheses. All right. So now we can use a root solver to find our theta value. So we'll do root scalar close. We're going to make our bracket directly in between 1 and 2. Alrighty. I don't know what that means. Solved. Alright, I'm going to see what's going on with that. Alright, I seem to just always make the same stupid mistake that ruins everything. We never returned anything from what our function is. Beautiful. Alright, so then our theta would be equal to, the root. Does that pull the right value? Okay, beautiful. So we can plot this. I saw in the example problem that they plotted it, but all that it asks us to do is find our minimum reflex ratio. So I guess we'll plot it, but it's not necessary, I don't think. We'll need our theta plots for our x-axis. So that's not what we want. We want it to go from, I think, point 4 up until, we'll do 3.1. I guess we can do 100 spaces in between. And then our UW plot is going to be equal to theta in theta plots. All right, so then fig equals make subplots. I don't know what all of that is. Goodness gracious. Fig dot add scatter x equals our theta plots, and All right, so here's our plot of this. I'm not quite sure why we need to do that, but we did it anyway. So then let's finish this up and solve the question. So we have our value for theta, and that would allow us to find the value of V that would give us our minimum reflex ratio. So V would be equal to NP dot sum. That would be alphas times what we're pulling out of the distillates. So that's just going to be, so I guess dxd. That is our RD times ZF. Is it RD times ZF? Yeah, it is. ZF. Okay. So then times dxd, and it's divided by alphas minus theta. Yep. Right, and then R is equal to V divided by NP dot sum terms minus 1. R turns out to be 1.16. So that is our minimum reflux ratio, and that wraps up separations homework 4.